Yo, welcome back to Tell Me About Again. Today we're talking to Dr Amary Triaud, who works on the Trappist 1 solar system, about how he finds these planets. How do you find these planets then?
So you first select the type of star that you want to find planets around, because again you have billions of stars you could choose from, so you have to choose some. And then what you do is that you spend time on each of those stars, you just wait. So the method that we've used to detect the Trappist 1 system was to wait for the planets to pass in front of it. And as they do so, they cast a shadow. You have the star and then the planet passes in front of it. If the planet were to orbit the star in that way, then it would never pass in front of it and cast a shadow. So for every planet that we detect, there's actually a lot more than we don't know about.
Oh, okay, so it's like you actually see the shadow.
Well, we see that the star becomes fainter. So if you place something like Jupiter in front of the sun, Jupiter is 10 times smaller than the sun, and they will cover an area which is only 1% of the total area of the sun. So you will have, the star will go fainter by 1%. We don't actually see the planet. We deduce from the light that we receive from the star that the planet must be there. And so far, most of the techniques work like that.
Then can you calculate things about the orbit?
So yeah, the orbit, so like when the transit repeats, that would be the orbital period. If you know the mass of the star, then it's telling you, you know, the distance that the planet is at from the star. Then for the composition you would need to, of the planet, you would need to measure the mass in some way. So in Trappist 1, what's really cool is that the planets are exchanging orbital energy between each other. They're so close to one another and close to a special configuration that sometimes the orbital period is a bit longer, sometimes a bit shorter, depending on which planet, and that interaction is telling us the relative masses of all the planets. So we have a good idea that the composition there is rocky, likely it has the same density as rock on Earth. And then for the atmosphere, what you do is, again, is a slight deviation from this transit technique, this shadow technique. You actually look for a shadow within the shadow. Say a planet like the Earth has a capacity to store blue light. That's why we have blue sky. Well, maybe not in England, but that's why the sky is usually blue, and why sunrise and sunset is red, because all the blue light got stripped and stayed at midday, essentially. Only red light goes through the atmosphere. So if you were to look at a planet using a blue filter, as it passes in front of the star, it would look like it's more opaque, because the blue light doesn't reach the detector anymore. And so what it comes down to is measuring the size of the planet. By measuring the size of a planet as a function of color or wavelength, then we deduce what chemical species are within the atmosphere. It's all about deduction. It's actually really quite cool.
That was really cool. Thank you so much for watching. Like, subscribe, turn notifications on. I'm going to stop commanding you. If you have any professors or people that you would like us to talk to, get in contact with us and we'll hit them up as soon as we can. Contact information is down below, so hit us up.